Hi everyone. I thought in this video I will show you a quick demo on how to get the shortest path between two faces on a mesh. So let's get started. The first thing that I'm going to do is hide the final result and start from the beginning. So what we're going to do is drag and drop a torus, for example, as an example mesh. You can get it from mesh torus in here. And when it is selected, if you do something like objects in, there are a couple of methods for that, a couple of nodes for it. And instead of drop here, I think it will say like get or something like that, or select. And when you click on that, it will bring the torus in. As you can see here, it's already selected. So after that, we will connect this to topology by geometry. So we feed it the vertices, the edges, and the polygons become faces. And out of topology by geometry, it will automatically give us the correct corresponding topology. So in this case, because it is a closed volume, a closed solid, or a closed mesh, it should give us a cell. This is the equivalent of a solid in Topologic. Now, the idea is that we create a graph of that cell, a graph of the faces, which is called the dual graph, that connects all the centers of the faces to each other. But topologically speaking, the dual graph of a cell is a single vertex that represents the center of that cell. So how do we get a wire that represents the connections between the faces? The trick is to get a subtopology of that cell, which is called a shell. So a shell is a grouping of interconnected faces, and the dual graph of a shell is a wire that connects these faces to each other. So this is exactly what we're doing here. We're getting a subtopology, which is called shell, and we are feeding it to graph by topology. So if we hide the torus, first of all, and we show the actual cell. So here is actually the topologic cell. It's identical, obviously, to the original. And I'm just choosing to draw it in wireframe, but if I connect the faces, you'll notice that it is complete. So let's go ahead and hide this. And then what we are going to do is, as I said, get the shell out of it and then do a graph by topology and just choose the simplest option here, which is just a direct connection between the faces. So if you want to see what this graph looks like, you can get its topology, which will be a wire basically, or a cluster sometimes, but it will be like a kind of a geometric entity, and then convert it to geometry, and then let's go ahead and show it. So what you see here is not the actual original torus, but a dual graph of that torus, of the shell of that torus, where the vertices, these yellow dots, represent the centers of the faces, and the green lines represent adjacent edges. They connect to each other. Once we have this type of data structure, we can find the shortest path between any vertex to any other vertex. And that's what we're going to be doing next. So how do we do that? You can get all the vertices of the graph by doing graph.vertices. So in this case, we are getting 576 vertices, and I have chosen to flatten them in order to feed them to the other nodes. And I'm creating two vertices. I'm specifying their actual x, y, z and coordinates, and then finding the nearest vertex from this graph. Now, why do I do that? Because when you update the Sverchok graph or run it again, graph.vertices will change order. They are not guaranteed always to be in the same order. So if you are just simply choosing two vertices by index, let's say take the index 0 and index 100 and connect them, those two vertices will change. And so you will get a different result every time you run it. So if you don't want that, the best thing to do is figure out what is the XYZ of the vertex that you are interested in, and then find the nearest one to it, and then find the shortest path. And this is exactly what I'm doing here. So vertex by coordinates, type in the XYZ, find vertex.nearest vertex from a list of vertices. So we feed it the graph vertices, and the one we're interested in, it will give us the nearest one to it. And then once we have those two vertices that we are interested in, drag and drop a graph.shortest path and give it the graph, the original graph from here, the two vertices. We don't have any dictionary, so we don't need vertex edges, vertex keys and edge keys. And then we draw the result, and this is the final result. As you can see here, let me go ahead and hide the original wireframe here for the topology of the dual graph, and let's show the actual original torus, and let's not do the polygon so that you can see it better. So this is the shortest path between this point and this point here. So let's go ahead and exercise this a little bit. So if we change the coordinates here, we should start seeing the shortest path update. Let me give you a feel for how fast it is. So let's go ahead, change these. It's not bad, quite good. And this one as well. It's not using some kind of sophisticated nearest vertex, it's just doing, I think, a bubble sort, so this could be improved perhaps. And you can see it's calculating the shortest path. That's it. I hope you enjoyed it. Thank you.